Welcome to ePathshala lecture series in computer science. This course is on operating systems and today's class we will learn about process synchronization. The learning objectives of today's class is that to introduce the critical section problem and to understand solutions to the critical section problem. We have learned earlier about cooperating processes. So, what are cooperating processes? They are processes that share data either directly or through files. So, when two processes they are sharing some common data structure or a common file, then the data that they share should not result in inconsistency. So, when two processes concurrently access the data, it should not lead to inconsistency. So, maintaining data consistency requires some mechanisms such that there is an orderly execution of the cooperating processes which are accessing that common data structure. So, we have already seen a shared memory solution to bounded buffer problem. In an earlier class, we learnt about a bounded buffer problem where you have a circular array of buffer in which items are placed by a producer and consumed by a consumer, and the solution that we have learnt there did allow us to place only n-1 items. So, this is the solution that we learnt in an earlier class. You have a shared data, you have an item and you have a buffer in which items can be placed. The size of the buffer is some buffer size, it is defined as 10. And you have two pointers in and out which are defined and are initialized to 0. So, initially this in and out point to the same location that is equal to 0, and then the producer produces items and places into the buffer. It will check if the buffer in +1 modulus buffer size is equal to out, then it means that the buffer is full and the scheduler cannot place the item and it will be waiting. If the buffer is not full, then the scheduler places the item into the pointer pointed to by the in pointer, and then it will increment the in pointer by 1. And when the buffer is full, as you can see, the condition is that in +1 mod buffer size should be equal to out. And in the next, for the consumer, the code will look something like this. It will first check if in is equal to out. If in and out point to the same location, then it means that the consumer cannot consume, the buffer is empty. And if the buffer is not empty, then it can remove the item that is placed in the buffer pointed to by out pointer and it is consumed by the consumer. After consuming an item from the buffer, the out pointer is incremented. And this solution to this bounded buffer problem that we had seen does not allow us to place all n items into the buffer. You can place only n-1 items to the buffer. So, what is done? Try to give a solution where all n buffers are used, but that is not a simple solution. So, we will try to give a solution for that, and that is being provided by a variable called a counter. So, introduce a variable called a counter which is shared between the producer and the consumer, and the counter variable is initialized to 0. And each time the producer places an item, the counter variable is incremented, and each time the consumer is consuming an item from the buffer, the counter variable is decremented. So, here you can see the data structures that are being used in this solution. You have an item which is defined as a structure, and you have a buffer into which different items are being placed. You have an in pointer, you have out pointer which is pointing in points to the location from where, location into where the producer places the item, and the out pointer points to the location where the consumer is consuming the item, and counter is this common variable that is shared between the producer and the consumer. And this is the one that maintains a count of the number of items that are placed in the buffer. So, we look at the solution for the producer process now. The producer process checks if the value of counter is equal to buffer size. If the value of counter is equal to buffer size is the number of buffers placed in that, number of buffers present in that bounded buffer, and if it is equal to buffer size, then you do nothing, the producer waits because the buffer is full. If the buffer is not full, the producer places the item into the buffer pointed to by the location in, and then it increments the in pointer, and the counter is incremented now by 1 because one more item has been placed into the buffer. So, this is the code for the producer. So, where it places the item into the pointer produces by the pointer pointed to by in, but the counter is the variable that maintains the number of items that are placed into the buffer. And similarly, if you look at the consumer's code, the consumer first checks if the buffer is empty or it has something to pick from. If the buffer is empty, the counter variable is checked, the counter variable will be 0. So, as long as counter variable is 0, the consumer cannot consume, it will be waiting. And if the counter variable is not 0, then it means that there is some element or there is some item present in the buffer, and it will remove that item that is pointed to by the out pointer and places into this next consumed variable. And the out pointer is incremented by 1. This now points to the next location from where the consumer can consume. And the counter variable is now decremented. Now, it means that it has removed an item from the buffer and the value of counter is decremented. Now, here you can see that this counter variable is being accessed by both the producer as well as the consumer. The producer increments the value of counter and the consumer decrements the value of the counter variable. And so, now this counter variable is a shared variable between the producer process and the consumer process. Now, the producer and the consumer are cooperating processes which share this common variable counter. Now, we will see what kind of problem can arise when this counter variable is being accessed by the producer and the consumer. So, you see that the statements counter plus plus and counter minus minus must be performed atomically. What is meant by executing atomically? See, this counter plus plus that is being incremented by the producer should finish, and only then the counter minus minus that is decremented by the consumer should be executed. That is, there should not be any interleaving of instructions in between. We will see how interleaving can happen. Say, for example, you have this counter plus plus in the producer's code. And how this could be implemented in machine language is that you will have a register onto which the value of this counter is being copied, and then the contents of this register is incremented by 1. And then after incrementing the contents of the register, the value of the register is now copied back to counter. So, here you see that even though this is just a single statement in the producer's code, in turn it is being executed in 3 different instructions. So, first is copying counter onto register, then incrementing the register's values, and then copying back the register onto the counter. Very similarly, if you look at this counter minus minus statement in the consumer side, you find that the value of the counter will be copied to say another register or a register 2, and then the value of the register will be decremented by 1, and then you copy back the register's contents to the counter. Again, the single statement counter minus minus is not executed in one single instruction, it is being executed in 3 different instructions. Now, there is a possibility of interleaving of these instructions. We will see how it will happen. Even though the producer and the consumer are 2 different processes, if they try to update the buffer concurrently, if they try to update this counter concurrently at the same time, it is quite possible that the assembly language statements corresponding to that particular one statement, counter plus plus or counter minus minus, can get interleaved. So, interleaving will now depend on how the producer and the scheduler processes are, I repeat again, now I repeat again. So, now the interleaving depends on how the producer and the consumer processes are being scheduled, depends on who is being scheduled first, who is being scheduled next, etc. and so on. So, we will see this example of how the value of counter can be manipulated depending on how the producer and the consumer processes are being scheduled. Assume that the value of the counter is initially 5. Now, say assume that the producer does a counter plus plus and the consumer does a counter minus minus. So, finally, what should be the value of the counter at the end of an increment and a decrement? It should remain the same, it should remain as 5. But it is quite possible that the value of counter can come to 4 or to 6. We will see how it happens that way. See, producer executes the statement first counter plus plus, and that in turn has a copying of the counter value to register 1. So, 5 is copied onto register 1 and then register 1 should be incremented. So, the register 1 is incremented by 1. So, the value of register 1 becomes 6. Then now there is a context switch. Say the CPU time of this producer gets over and the consumer is now given the CPU. So, when the consumer is given the CPU, it will execute its code. What does the consumer have to do? It has to execute counter minus minus. But this counter minus minus has got 3 different instructions to execute. So, it executes the first instruction corresponding to counter minus minus. What is that? Counter register 2 is equal to counter, or the value of counter is copied to register 2. What is currently present in counter? It is only 5. So, 5 is copied on to register 2. And say the consumer executes the next statement also, that is register 2 is equal to register 2 minus 1. That is, the value is decremented by 1. So, the value of counter is decremented by 1 and here you see that the value becomes 4 in register 2. And then again there is a context switch. So, the producer now gets the CPU. Now, producer has to execute the last instruction of that statement counter plus plus, that is nothing but counter is equal to register 1. The value of register 1 is copied to the counter. So, counter now gets the value. What should be the value present in the register? It is 6, that is copied onto counter. The counter now becomes 6. And then the consumer executes. Consumer has got one more instruction to complete, that is register 2 should be copied to counter, and now register 2 is copied to counter and you have counter equal to 4. So, finally, what is the value of counter now? It is 4. But what should have been the value of counter? It should have been 5, because one increment had happened and one decrement had happened. So, 5 plus 1 6 and 6 minus 1 should have been 5. But now unfortunately here you see that the value of counter has come to 4, which is wrong. So, what happened here? Here this variable counter was accessed by both processes, the producer and the consumer, which are concurrent processes which try to operate or which try to access the same variable counter, which has not been safeguarded, and hence there is no consistency in the value. So, what is done? This counter plus plus and the counter minus minus should be safeguarded properly, and this condition is called a race condition. That is a situation where several processes access and manipulate shared data concurrently is called a race condition, and the final value of the shared data depends upon which process finishes last. That is what we had seen in the problem that we had seen. So, because the the consumer process finishes last, the value of counter was 4. Suppose if the producer had finished finally, then the value of counter would have been 6. Okay. So, to prevent these race conditions, the concurrent processes must be synchronized. So, in this topic actually we learn how the synchronization can be achieved. And now we define this critical section problem. So this critical section problem comes into picture when there are n number of processes and all the processes are competing to use some shared data which is common to all the n processes. And each process has got a code which is called the critical section, and that critical section of code is the place where each of the process is accessing that one common shared data. So in the example that we had seen here is you have two processes, the producer and the consumer, and both the processes have one critical part of code. For example, in the producer process you have that counter plus plus. Incrementing the counter value is the critical section of code in the producer, because that is the place where the producer is accessing that common data. And for the consumer, counter minus minus is that critical section of code. Only in counter minus minus the consumer is trying to access the common shared data. So here each process, the producer as well as the consumer, has got a code of their own called the critical section, in which they access that one common shared data. So the problem here is that you need to ensure that when one process is executing its critical section, no other process should be allowed to execute its critical section. And again repeating with the same example, producer and consumer, when the producer is executing counter plus plus, the consumer should not execute counter minus minus, and vice versa. If that is possible, then your problem will be solved. So this problem is the critical section problem, where you have a critical section of code for each process, and when one process is executing in its critical section, the other process should not be allowed to execute its critical section. So how do you have a solution to a critical section problem? And when you are looking at a solution to a critical section problem, there are three different things that you need to look at. So any solution to the critical section problem should look at or should be able to solve these three problems. One is mutual exclusion. What is mutual exclusion? When one process is executing in its critical section, no other process should be allowed to execute their critical section. Now when I explain it in terms of this producer consumer problem that we have seen, when the producer is executing counter plus plus, the consumer should not be allowed to execute counter minus minus. So when a process is executing in its critical section, no other process should be allowed to be execute their own critical section. So a solution to any critical section problem should be able to solve this, or should be able to achieve this, should be able to achieve or should be able to ensure mutual exclusion. And the second condition that a process or a solution to a critical section problem should ensure is progress. What is progress? If there is no process executing in its critical section and there exists some process that wish to enter critical section, then the selection of the process that will enter critical section cannot be postponed indefinitely. Say assume you have two processes P1 and P2, both are currently not in their critical sections and both want to enter critical section. They are waiting to enter their critical sections of code, and now there should be some selection should be done between these two processes P1 and P2 as to who will enter critical section next. This selection should not be postponed indefinitely. You can't make the two processes wait indefinitely to enter critical section. There should be a way in which one of these two processes can enter critical section immediately. And the next third condition for a solution to the critical section problem is bounded waiting. So bounded waiting, a bound should exist on the number of times that other process is allowed to enter the critical section after a process had made a request to enter its critical section and before that request is granted. What does this mean? Say you have P1, P2, P3. There are three processes who want to enter critical section. So P1 has requested to enter critical section, P2 also has request to enter, P3 has request to enter. All three are requesting to enter critical section and waiting. Assume P1 is first allowed to enter critical section, and then P1 comes out of critical section, and now P1 again wants to enter critical section. Now this P1 should not be allowed to enter critical section before P2 and P3 have entered their critical sections, because P2 and P3 also had requested earlier before even P1 trying to enter critical section the next time. Okay, just because one process got the system and it's allowed to enter critical section once, it should not be allowed to enter critical section in many number of times, and these processes should not be made to wait, say P2 and P3 should not be made to wait for a long amount of time, or the number of times or the amount of time for which P2 and P3 have to wait after they have requested to enter critical section should be bounded, or there should be a time limit for which P2 and P3 wait before enter critical section. And here in this we assume that each process executes at a non-zero speed, or there is some speed with which the process execute, and there is no assumption concerning the relative speed of the different processes that are executing. All these are assumptions that have been made, and many attempts have been done to solve this critical section problem. So we will look at one attempt that have been used to solve this critical section problem. This was the initial attempt that have been done. So in this attempt, what is done is that you have two processes P0 and P1, and a solution has been given to this problem of critical section when there are only two processes. And if you look at the general structure of any process that are willing to enter critical section, will look something like this. That is, there will be a critical section of code, and there will be one section called the entry section, and in this entry section is a place where a process will request to enter critical section. And then after this critical section of code gets over, there is an exit section which the process will execute after coming out of critical section, and then you have the remainder section of code. So if you look at this solution, the structure of any process will look something like this, and there can be two processes P0 and P1 who have a similar structure, and the processes will share some common variable so that they can synchronize the action. So now we look at one algorithm that gives a solution to this critical section problem, and in this algorithm the common variable is a variable called turn, and you have the structure of each process being given this way. So the process Pi will execute like this: while turn not equal to I, it will just keep on waiting. So this is the code for process Pi. It will check if the value of this variable turn is equal to I or not. As long as it is not equal to I, its ID, it will keep on waiting. And if the value of turn becomes equal to I, then it can enter critical section. After coming out of critical section, you find that you have a statement called turn equal to j. So this turn equal to j is being made after this process I comes out of critical section. So what does this process I do? After coming out of critical section, process Pi will change the value of turn equal to j. So the common variable between Pi and Pj is this turn, and this turn is initialized to 0 first. Now we will see an example of how this works. So for mutual, we will see whether this algorithm satisfies mutual exclusion. And as I told you earlier, this is an algorithm for two processes. It is a solution to solve the critical section problem when there are only two processes. So you have this common variable turn between the two processes P0 and P1. So initially the value of turn is kept as 0, and P0 and P1 both want to enter a critical section. So both of them, they try to check the value of turn. So while turn not equal to y, that is a statement that is executed by P0 as well as by P1. So P0 finds that the value of turn is equal to y. So P0 finds that the value of turn is equal to 0. So P naught can enter critical section, but while P1 checks the value of turn, it finds that the value of turn is equal to 0 and is not equal to I. What is I for P1? It is equal to 1. So the value of turn is not equal to 1 for P1. So it checks this common variable turn, finds it to be 0 and it just keeps on waiting. At the same time, P naught enters critical section. So here we find that when one P naught enters critical section, P1 cannot enter critical section because the value of turn is equal to 0, or it can take only one value, and based on that value the process can enter critical section. And when P naught exits critical section, it will change back the value of turn to be equal to 1. Now this process P1 who is waiting finds that the value of turn is equal to 1 and it can enter critical section. So P1 enters critical section, and then P naught, when P1 is in the critical section, P naught checks the value of turn, it finds that the value of turn is equal to 1 and P1 waits. So thus mutual exclusion is satisfied, that is when one process is in the critical section, the other process is not allowed to enter critical section. Now we will see if progress is satisfied for this algorithm. Initially say the value of turn is equal to 0 and P naught checks the value of turn and it enters critical section, and after coming out of critical section it checks the value of turn, it changes the value of turn to 1 and then it checks the value of turn, it finds the value of turn equal to 1 and then it wants to enter critical section the next time. Now what happens? See, P naught had the value of turn equal to 0 initially, and after coming out of critical section it changes the value of turn equal to 1. But P1 in the meantime it does not want to enter critical section at all. So this P naught, if it wants to critical section the next time, it cannot enter critical section the next time. Why? Because P1 turn, the value of turn is changed to 1. Unless P1 enters critical section, P naught cannot enter critical section. So here you find that the solution has given a strict alteration between P naught and P1. So if P naught enters first, P1 has to enter second, and only then P naught can enter, and then P1 can enter, and so on. So if P1 does not want to enter critical section, then P naught cannot enter critical section the next time. So we find that progress is not satisfied. So after P naught had requested to enter critical section, it is not allowed to enter critical section, or it is made to wait indefinitely. Hence progress is not satisfied in this algorithm. So this algorithm satisfies mutual exclusion, but it does not satisfy progress. So this is not a complete solution to the critical section problem. So I conclude with this for today's class. We have other algorithms which are solutions to the critical section problem, which give solution to the critical section problem satisfying all the three conditions: mutual exclusion, progress and bounded waiting. That we will continue in the next class. So summary of today's class: we learned that when cooperating processes share data, then some kind of synchronization have to be provided, else it may result in inconsistencies of the shared data. We introduced you to this critical section problem. You learned what this problem of critical section is, and then we saw one solution to this critical section problem, but that solution did not satisfy all the three conditions required for a solution to the critical section problem. It solved, or it only satisfied only the mutual exclusion condition. The other condition, progress and bounded waiting, are not satisfied. References. Thank you.